Hello everyone, welcome to MSc 351-1, Physics of Materials. We're going to cover the topics in the book by Kasap, Principles of Electronic Materials and Devices. The course will start with Chapter 2, Classical Electrical and Thermal Conduction in Solids. In these lecture videos, we will cover the essential concepts needed for this course. For a detailed explanation, including derivation, I strongly encourage you to read the textbook. It's quite good. In this section, we discuss the classical theory of metals using the Drude model, where we treat electrons as an ideal gas of charged particles that travel through the solid randomly, bouncing off the atoms. The Drude model is a great way to give us a microscopic and mechanistic understanding of electrical properties in solids. We know electrical resistance from Ohm's law, which is used when we have a current I going through a resistor with a resistance R. The voltage difference across the resistor is delta V, or simply we say V equals IR as the voltage drop equals the current times the resistance. Now in material science, we are interested in intensive quantities, which are the quantities felt by the material at any particular point, as opposed to extensive quantities, which depend on the size and shape of an object. The voltage, for example, is an extensive quantity. It's due to the difference in electric potential from one end of the sample to the other. Now from physics, we know that the voltage is equal to the electric field times the distance L across the sample. And so the electric field E is really the intensive quantity. Similarly, rather than the entire current I going across the whole sample, the intensive quantity is the current density J, which is the current divided by the cross-sectional area A. We end up with the intensive Ohm's law, which is the electric field equals the current density times the electrical resistivity. Resistivity is measured in ohm meters. Resistivity, unlike resistance, is a material property that is independent of the sample size and geometry. Resistivity can be extracted from the measured resistance times the cross-sectional area A divided by the length of the voltage drop. The electrical conductivity, sigma, is simply the inverse of the resistivity. The common form of Ohm's law using intensive quantities is current density equals conductivity times the electric field. The Drude model is based on an analogy of electrons with classical particles that are free to move. Sometimes we call it a classical gas. Electrons are treated like ping pong balls bouncing around. The concepts we will use can even be applied to water flowing in a pipe or cars driving down a highway. Let's think of our conductor as this large yellow cylinder. Inside that conductor, we have negatively charged red electrons that are all on average moving to the right. For now, let's think of the electrons as having the same average velocity we call the drift velocity. An important equation that we will use from this classical model is that the current density J is equal to the electric charge times the density of electrons N times the velocity of these electrons V. Recall that the current density is defined as the amount of charge passing through a cross-sectional area A in a time delta t. Now consider the volume of electrons that will all pass through the area A. In a time delta t, the electrons will have traveled a distance equal to the drift velocity times delta t. So the number of electrons passing through A is the number of electrons in this volume, V times delta t long, and cross-sectional area A. Now the charge passing through is the charge per electron times the number density of electrons times the volume AV delta t. This makes a lot of sense in that we know that to have a large current, we would need to know how much each charged particle has, how many particles there are per unit volume, and how fast they are. For conduction along our wire, say along the x direction, we really only care about the velocity of electrons in the x direction. If the electrons are moving in the y or z direction, they're not contributing to the conduction that we measure in the x direction. Similarly, we are only worried about the average velocity because we are looking for the net conduction. Sometimes we will call this the net velocity as opposed to the speed of the electron, where the electron speed might be much greater than this drift velocity. The velocity from the speed of the electron will be in a random direction, not contributing to the electrical current. So we'd like to think of the electrons, the red dots, moving freely in a metal, such as copper, where we think of these large green circles as being copper ions and the electron is moving around in between the spaces between the atoms. Now these electrons are moving with a very large speed, which we call u here, but they don't get very far because they are constantly bumping into the atoms. They move diffusively like mass diffusion. Without a bias, such as a potential difference across the metal, there will be as many electrons moving to the left as moving to the right, and so the net drift velocity, given by the sum of all the electron velocities, will be zero. Now, in the presence of an electric field, the electrons are being pushed here to the right. Even though each time an electron hits an atom, it heads off in a random direction, it is pushed a little to the right. In the end, it will have traveled with a net velocity to the right. On average, the electrons end up in a position further to the right than they were at the beginning that can be described by the drift velocity. Each of our electrons in an electric field will be gaining a velocity, or accelerating, in the direction being pushed by the electric field for a certain amount of time until they have a collision in which they start over again. Some electrons will be accelerated longer than others, but on average there will be some average time between collisions, which we will define as the scattering time, tau. This average time will give them an average increase in velocity, which with proper averaging is found to be the drift velocity. Now we can relate this buildup of drift velocity to the acceleration and the force due to the electric field using Newton's laws. From F equals ma, we have A equals the electric force over the mass. This gives us a relationship between the drift velocity and the scattering time in terms of the charge and mass of the electron and the electric field. Here we introduce the concept of mobility as the proportionality constant relating how much drift velocity is produced from an electric field. Then from the above, we find that the drift mobility is simply the electric charge and the time between collisions divided by the mass. Because mobility is essentially a relationship between the net velocity of the particle and the force that is pushing on the particle to make this velocity, it is a fundamental property about the particle, and so we will be talking about mobility quite a bit in this class. Here we derive the Drude conductivity from the relationships we've had before. The current density in terms of the density of electrons, their charge, and the drift velocity. Also the definition of conductivity as current density produced from an electric field. Then we can replace drift velocity with mobility times electric field. We see that conductivity then is equal to NE mu, an expression we will use often. If we write the mobility in terms of tau, we get NE squared tau over m for conductivity. Thus the Drude model gives an expression for the conductivity of classical particles that move freely like atoms in a gas. The number density, charge, and mass are properties of the static system. So the Drude model tells us that the unique transport property of conductivity can be equally described by a mobility, how much something moves if you push it, or a scattering time, the time between collisions even when the particles are not being pushed. We have also introduced the concept of the mean free path, which is the average distance an electron will travel between collisions. It is simply given by the average speed of the electron times the average time between collisions. Keep in mind that this is the total speed, not the drift velocity. When there is no electric force, the average drift velocity is zero, but the electrons are still moving quite fast. We will show later that the speed of the electrons in a metal is typically on the order of 1% the speed of light. Kasap uses u for the average speed of the particles and v for the drift velocity to help distinguish them, but other sources will use different symbols.